our open challenge project this year, we tried to make a faster mind-controlled keyboard using motor imagery instead of P300.
Most EEG spellers show in random order all the letters that can be chosen and hope to get a P300 response when the letter you want is selected. But with imagined hand gestures, you could tell the keyboard which letter you want directly, and we hypothesized that this would make mind-controlled keyboards support seamless communication. Natural language processing would make typing even faster, being able to predict words and emojis to reduce the number of operations needed.
To develop MindType, we had to do a few things. We had to design a user experience to make the keyboard intuitive and easy to use. We used 3 different approaches to analyze EEG and allow for mind typing. Word and emoji prediction was used to make typing even faster. Our multi-threaded async architecture brought all this together and made streaming EEG and operating the keyboard work in real time without blocking each other.
Hi, my name is Carl.
Cyan,
Jeremy.
Hi, I'm Vitaly.
Musa,
Svare, Benedetta,
Rusty.
And we're the team behind MindType.
Alright, so what got you interested in neurotechnology and why did you join MindType?
Well, when first I was considering joining MindType, I was thinking about how complex our brain is and how we still know so little about it and about all the things that our brain could teach us.
So neurotechnology is still a rapidly developing field. We know so little about the brain, and so there's so much opportunity for research and for new ideas.
I liked that the field was interdisciplinary, so it had the field of social justice, cognitive science, and design, and I wanted more work to explore these fields, even if it was on my own time.
Neurotech is about as cool of an application for machine learning as it gets. And after watching a lot of Black Mirror, I figured, heck, I might as well do it. Yeah, I've been enjoying it. It's a great time.
For MindType, I worked on algorithm optimization. So by optimizing the algorithms, we just make it so that it takes less computing power and it goes faster. I refactored some code in the main algorithm, and I also converted some code to Python. The main time saver here were the Python functions, and what that did is it sped up the code by 4 to 5 times.
When it comes to the word prediction, we had 2 main things to choose from, either neural networks, including LSTM, or the simple n-grams. Overall, after evaluating the performance of the 2 and the complexity, we decided to go with n-grams, as the performance is slightly worse but insignificantly, and the complexity of n-grams is only a fraction of that of LSTM.
I focused on the calibration stages of the keyboard, and I specifically focused on P300 and the binary classification. Because of time constraints, I decided to make a first iteration that we could use for the usability tests afterwards. I wanted to use the calibration stage to teach the user on how to use the keyboard so they could start using it sooner. For the P300 stage, the setup screen would first instruct the user to look for a letter, and then show how this could be used to control the keyboard. I used a similar approach for the binary motor classification.
One of the main challenges was the fact that it was a bit hard to make it work in real time while not slowing everything down. And it turned out that there are some bottlenecks when it comes to performance, and we overcame it by using data structures that were modeled for this, such as trees.
We developed real-time analysis algorithms for 3 different EEG paradigms to increase chance of success. We tried to use the oddball paradigm by analyzing EEG for the P300 wave. For iteration 2, we explored binary motor classification and used left hand versus right hand as an input mechanism. We ultimately want to use 6-class motor imagery per hand to be able to select each letter with one operation.
So I worked on the P300 speller, in which we recognize P300 signals after an event stimulus. In this case, it was looking at a flash on our keyboard. So for us, we actually drew a lot of inspiration from Alexander Bereshant's work, where he uses a muse to easily identify a P300 signal. And for us, one of the challenges was that we had to use an older variant of the muse. And for me, that meant coming up with a new real-time framework for how we're going to receive those signals and also how to synchronize them with the markers and the stimulus coming in.
One of the most interesting paper we found is the one that controls a drone with using hand signals, whether to open your hand or not. We can integrate this one with our mind control keyboard by controlling the graphical user interface after getting the signal, which depends mostly on the value of mu wave from the C3 and C4 electrodes after we get them.
Yeah, so at first when we were doing multi-class motor classification, we used an approach using cortical current density estimation, but we ran into a lot of trouble with the source localization aspect, especially with pinpointing the dipoles. And we also found this cool paper by Cesar Marquez Chin, where he pretty much analyzed spectrograms of an 8-channel EEG tightly clustered around the premotor cortex, classifying 5 hand gestures. And so using an architecture inspired by a group from the University of Freiburg and using techniques that was used by Cesar Marquez Chin, we developed a deep convolutional neural network to classify 9 different hand gestures, 4 from the CCD paper and 5 from the Cesar Chen paper.
So when we classified with the LDA, we were getting very poor results, and upon observing the data, we saw that although we were visually seeing among the averages a recognizable P300 signal at where we expected it, when we graphed out the standard deviations, we saw that there was a systematically high standard deviation among all the signals. And one of those reasons is that we might be getting an offset between where we observed the data and where the stimulus actually happened.
So we actually got about we got approximately like 15% accuracy, and we think that this is due to some bugs inside our neural net itself. Another problem was just getting good data, because initially we wanted to mimic real-life conditions and have someone, with hair, without using any conductive solution. But that actually created a lot of noise in our data.
One of the ways to fix that might be to either use a convolutional neural network to be able to capture the difference in time of when those P300 signals occur. Or we can make multiple passes of the same data at different times, so we can capture the P300 where we might not expect it, but where it actually happened.
First, we want to make a very controlled experiment setting where we would ideally have someone without any hair and use as much conductive solution as we want, and essentially stabilize the headset a lot more to get better data.
I believe my favorite moment would be when we first got when I first got the whole process running. So the OpenBCI board connected to the USB, and then that connected to my laptop. And when I got the signals to actually print out properly.
So I didn't have one most favorite moment. It's most of the time sitting with the team, working with them, different backgrounds, different disciplines. We learn from each other, and we share our interests in neurotechnology and what are the latest news and the hot topics that are going on right now here.